Hello, everybody. This is the third part of our chapter 1.3, and we're going to talk about the linear combination in two-dimensional space, or R2. Okay, so let's just remind ourselves the definition of linear combination. If we have two vectors, v1 and v2, then linear combination is just product of each of this vector on appropriate number C1 and C2, which call weights, and then the sum of two of these products. Okay, so it's basically you recognize that each one of these components of the sum is just a simple linear combination of one vector, here v1 or v2. Okay, so let's just look at the geometric interpretation in two-dimensional space and try to figure out how to make this linear combination and when it works. So let's start with just a simple vector. We call it v1. So it's like 1 minus 1 minus 1, 1. And let's try to form a linear combination. And we know that we can do it by stretching or compacting this vector. For example, let's just stretch it twice. That will give us weight 2 and maybe 3 times 3v1. We can also do that in negative direction. So minus v1 is exactly the same as v1, but pointed in opposite direction. We can stretch it to minus v2, and probably not surprise you because we learned in the previous lecture that the linear combination of single vector forms a line. Okay, so does it work for another vector? Let's take the vector v2. It's probably like 2, 1. And conduct the same operation. We stretch it, and in positive direction, we stretch it in the negative direction. So it's kind of form a grid. So now let's explore a linear combination of this. So what's happening if we step in this grid? For example, if we step 1 unit in direction v1 and then 1 negative unit in direction v2, we will get the linear combination v1 minus v2. In other words, the weight c1 is equal 1 and weight c2 is equal minus 1. Okay, we can also, for example, step twice in our grid in the negative direction of v1 and once to the positive direction of v2. And that gives us a vector minus 2v1 plus v2, or the linear combination with the weight of v1 is negative 2 and weight of v2 is 1. And we don't necessarily have to step in the integer numbers. For example, we can move on this grid as fraction. For example, we can step 3, 2 or 1.5 in the direction of v1 and then 1 in direction of v2. So, and that gives us the fractional weight for c1 equal 3 over 2 and v2 is still equal 1. So as you can see, we can move a lot about two-dimensional planes, and we seems to always have some kind of linear combination. But how do we find actually numerical value for this linear combination? Okay, let's go actually to actual numbers and try to figure that out. For example, again, this is our v1 and v2, but now they're in terms of the numbers or the x and y coordinates, because we're talking about two-dimensional plane. And we will try to find the vector u, which forms by linear combination of 3v1 minus 2v2. And again, we start with a definition. It's always good to start with a definition. I always write it down. So we'll write definition of linear combination. And now we will just start matching our terms to find the actual values for the weights. For example, in front of the v1, there is a 3, which means that our weight c1 is equal 3. And we can do this for the second vector. In front of V1, there is a -2. So our weight C2 is equal -2. So we can then plug all the numbers for our weights and vector and conduct basic mathematical operation within vectors. Okay, let's distribute our weight inside the vector. So we basically multiply first vector by 3 and second by 2. Now we will do a subtraction of appropriate term. We subtract first row of the vector 1 from the vector 2, and we do the same with the second one. Okay, so we just do basic algebra, and that's give us a vector -7, 1, somewhere here. But if you think about it, it totally makes sense. We're making 3 steps along V1 in the positive direction and 2 steps about V2 in the negative direction. So it will be right here at the edge. Unfortunately, we cannot see it. Okay, that's nice. We can calculate the linear combination, but what if we need to do the other way around? What if we are given a vector and we try to find the linear combination? Let's just try to do this. So now we're given vector 1, 5, so somewhere here, and we will try to find the linear combination of V1 and V2 vectors, which give us that vector. In other words, we will try to find the weight which give us a vector u. And again, we start with a definition of our linear combination. And then we just substitute again. The process is very similar to what we've done before. We just now have C1 and C2 as 2 variables. Okay, so but we conduct the mathematical operation with vectors. So we distribute C1 in the first vector and C2 in the second vector, and then we add the components together, which give us something which looks probably very similar, which we saw in the chapters 1.1 and 1.2. We have a systems of 2 equations with 2 variables. The only difference that we have C1 and C2 variables, not x1 and x2 as we saw before, but that shouldn't really matter. The C is just the name of the variable. So we can, write something in echelon form, or we can do old, substitution. I'm kind of tired of matrices, so I'll go with old school and just use my second equation to express C1 in terms of C2. So now we have a C1 and we will substitute it into the first equation. And next is just an algebra. We distribute the negative sign and then combine the like terms, and we get the value of C2 is equal to. Great, so this is the time to go back and find C1 in terms of the numbers, which will give us C1 is equal 3. So now we have 2 weights, C1 and C2, so we can actually write our linear combination using these weights. So our C1 is equal 3, C2 is equal 2, so 3V1 plus 2V2 is equal our vector u, which happens to be 1, 5. So we have to go a little bit farther away from the grid to find it, but it seems to be working. Will it be work every time? Will it be true for every single vector? Can we find the linear combination of any point on the 2-dimensional plane? Or in other ways, we can ask, what is the span of vectors of V1 and V2? Because we know that the span is just the set of all possible linear combinations. And here, there is really no limitations for us because our weights can be fractional. Any point can be fine in terms of this weight. So here, all 2-dimensional plane is included is our span, or our span is whole R2. Okay, this is all for linear combinations R2. Next time, we will talk about linear combination in Rn.